Hello. I thought I would go through a few more of the sections of solutions from that Path to a 5 packet. Um, I first, though, I remember that before we left at school, one of you classes, I think it was B2, but I'm not sure, somebody was asking me if my online work would include math jokes. And this one, as we get started, is a Mr. Knapp original. I thought of this one myself, so it goes, why were 6 and 7 afraid to multiply? And the answer is 6 and 7 were afraid to multiply because they lacked the fortitude. Huh? See what I did there? Anyway, back to the calculus. I did 1 through 7 on the standard the other day. That should have been in a separate video. Standard 8 starts with instantaneous rates of change. That's basically code for derivative. You should definitely notice the 3 different versions of derivative that they show here. This version specifically that you see me circling here, this is going to specifically find the derivative at point A. This more generically will find the derivative of a function at any location x. Do notice what we're taking the limit as x approaches a or as h approaches 0. If I start looking at some of the questions, I'm not so much concerned with question 1. Number 2 is definitely the sort of thing that you guys should recognize. You should see over here an entire function, and over here you see the entire function but with x plus h instead of x. That's a code that we're looking at this limit of x, f of x plus h kind of thing. So that's why we know this is the derivative of 6x squared minus 2x plus 7. With 3, this is a little bit tricky as a multiple choice question. Statement 2 is our direct derivative limit from the top of the page up here. 1 and 3 really look an awful lot like it. Number 3, there's 2 things wrong with it. First off, this would be the derivative of f at x, not a. And second of all, it would have to happen as h approaches 0 for this form, not as x approaches a. For number 1, we have the same issue that this has x approaching h. If this limit were as h approached 0, number 1 would also be a correct answer. But as it stands right now, 2 is the only thing that we're looking at that works, and that's why they have B circled. If I move on, number 9, tangent lines, that's something that we've worked an awful lot on throughout the year. Some of this should be pretty standard for you guys. Do remember the derivative gives you the slope of the tangent. The original function gives you a location on the graph. So number 1, they took the derivative using the power rule, plugged in -1 to the derivative to get the slope. That slope has to be a number. In terms of getting the point on the curve, they had to take -1 and plug into the original f of x, because that's what determines location. F is location, F prime is slope. Number 2, since they're talking about slope of a tangent again, they gave you 2 points. So we're just looking at change in y over change in x to get an answer. For number 3, this is a little bit trickier. This is the backwards version. They are talking about the derivative equaling 1. Where is the slope of the line 1? So if you skip to the end, you can see already in their equation they have a slope of 1. To figure out where that happens, they needed to take the derivative and say that the derivative equals 1 and solve for x. This would have been solved by graphing on your calculator. That x value drops right into your equation for x. In order to find the y coordinate, again, derivative gives slope, original equation gives location. So plugging 0.237 into here is what got them their final answer for y. Do make sure, it's a very common mistake on this sort of problem, to get this x value and then plug it back into the derivative, and then you end up with a y coordinate of 1, but that's the slope. You're just kind of making a little bit of a circular loop there. Make sure you're using the right function for the right thing. Number 10 talks about horizontal tangents. We talked about those both as tangent lines and also as about things that were useful when we talked about increasing, decreasing, max, min stuff. Directly, a horizontal line has a slope of 0, so we want to make the derivative 0. You can see in both of these parts of number 1, they took the derivative set equal to 0 solved. These y coordinates, again, don't come from plugging into f prime. We already know if I plug into f prime, I'm getting 0. Those y coordinates come from plugging into f. Same thing with b, except there's no solutions. Do notice the way they differentiated b, turning it into 2t to the negative third and a power rule? On some of our recent work in class, when you've had to anti-differentiate things like this, some of you guys have gotten confused and forgot about turning things into a negative exponent. So make sure you're thinking about those negative exponents. Number 2, they gave you h prime. So if we set h prime equal to 0, that's when the numerator is 0 and they solved. Number 3, again, they gave you the derivative. So they set the derivative equal to 0 to find where we have a horizontal line. And they made you do some nice unit circle work, which I know everybody loves. Continuing on here, standard 11. This I'm not super concerned about. As a matter of fact, I'm not even going to look at question 2 or question 3. The idea behind a linear approximation is to get an equation for the tangent line and then just use the tangent line to approximate the function instead of the actual curve itself. Here, we decided that this is near the x value of 2. So we got the 0.2 comma 3 halves that you can see dropped into our point slope formula. We changed this again to a negative exponent, took a derivative with the power rule, and plugged in 2 to get a slope. This is now the equation of the line tangent at 2. So whether we're at 2.1 on the curve or 2.1 on the tangent line, we should be pretty close. Those should be very, very similar values. And so that's what they did, is they plugged in 2.1 into the tangent line equation and solved for y. Where we've seen this in class is I showed it to you guys right before we left for this little Corona hiatus. I showed this to you guys in the context of differential equations on the slope fields day. We also talked about this back in the first semester. You see this a lot with applied problems. Not so much in a problem like this, but a lot of times in a problem where they give you a big table of values. This means something. Can we estimate how many leaves were on a tree after 3 days instead of 2? Something like that. That's usually where you get this a little bit more often. If I continue down, standard 12 on this packet, derivatives of inverse functions. You guys might remember this from last semester. This was something that was kind of weird, where you guys had a formula that I gave you. You can see it right here. The derivative of an inverse is f prime of f inverse of x. You do have to remember that a function and its inverse go in opposite ways. So in number 1, when they tell you big F of 2 is 3, that's also telling you g of 3 is 2 if f and g are inverses. So then using this formula to find the derivative of the inverse, we needed f prime of g of 3. So that's f prime of 2, because we know g of 3 is 2. How do we find f prime of 2? Let's take f. You can see me circling it. Move down here. We can find f prime with the power rule. And then plug in x equals 2 to get 4. That's where we get 1 over 4. Question 2 is done the exact same way. Since 1 comma 2 is on f, 2 comma 1 is on g, that means g of 2 is 1. So in this formula, the inverse at 2 is 1. So we need to take the derivative of f and plug in 1. And that's the bottom of the fraction. Okay, let's see here. I will also take a quick look at 13, and that'll be where I stop for this video. I'll try and get some of the other standards in another video. Here they're talking about differentiability implies continuity. This is one of those important things we've talked about, that if a derivative exists, a function must be continuous, guaranteed. Differentiable is a strong statement. It does not work the other way. We can be continuous with no derivative. Our standard example of that is the absolute value function, where we have that sharp corner. In question 1, you might notice that this expression that they give right here, this limit is the limit definition for the derivative at 2. So when they say this limit is 5, it's immediately telling us the derivative at 2 is 5. We have to be differentiable if we have a derivative. And because we're differentiable, we must be continuous. 1 and 2 are both true. Just because f has a derivative doesn't mean the derivative is continuous. That gets a little bit weirder. Number 2 talks about a piecewise function, that they want to be both continuous and differentiable. We talked a lot about continuity with this sort of thing, that we need the function to be this close to the same thing no matter which side we approach from. So they plugged in 1 for x and got 1. They plug in 1 for x here and they get 1 plus k plus p. And then this all reduces to k plus p equals 0. That'll make the function continuous, but not necessarily differentiable. So what we still need to go and take a look at is, how do we make the derivative work? Well, to avoid one of those absolute value sharp corner things, we need to make sure the slope before 1 and the slope after 1 are the same. So that's where they took the derivative here with the power rule to get 2 minus 2x. They take the derivative here to get 2x plus k, and we want to make sure those are also the same. When x equals 1, we get 2 minus 2 is 0. When x equals 1 on the bottom piece, we get 2 plus k. That let them solve for k as negative 2. Going back into k plus p equals 0, let them solve for p. Okay, I hope that was helpful. As usual, if you guys have any other questions, please email me. Use the discussion board on Canvas. Please keep checking your student email. Please keep checking the Canvas page for various updates on things. And if you have any questions, let me know. Good luck to you all.